Hello and welcome back. In section 5.1 we get to work on antiderivatives and indefinite integrals. So we'll start with just a hypothetical. So we'll consider f of x is x to the fourth. So I'm going to give you a few options and you're going to tell me which functions have f of x as a derivative. So we'll do, these are cap f of x, 1/5 x to the fifth, b cap f of x, 1/5 x to the fifth plus 7. C will be cap f of x, 1/5 x to the fifth plus 9,374. And D will be cap f of x, 1/5 x to the fifth minus pi over 91. So go ahead and pause it and see which of these four have f of x as their derivative. Okay, welcome back. Hopefully you noticed that all four of these had had lowercase f of x as their derivative. Really, all of these just differ by a constant. So how to sort of write up what we have, since there's, you have probably figured out, there's an infinite number of possibilities that I could have for what constant I could keep adding on to 1/5 x to the fifth. So the symbol for undoing a derivative, we have this little sort of elongated s-looking guy, our integral of x to the fourth dx. So this is just saying, okay, which variable would be 1/5 x to the fifth, and then we just put the general plus c, plus an arbitrary constant. So this is actually a family of solutions. Not a single solution. So this covers all four of these guys and the uncountably infinite number of other cap f of x's that would exist out there. So any of our derivative rules we can just sort of hit the reverse gear on. So for example, if we recall that the derivative with respect to x of x to the c is c times x to the c minus 1, then equivalently we can say the integral of x to the n times dx, we would increase the exponent by 1, as opposed to when doing the derivative we would decrease it by 1, and then we would have to multiply by 1 over n plus 1. So that way when I multiply the exponent with the coefficient, I get the nice, neat, pretty implied 1 here. Similarly, derivative with respect to x of e to the x is just e to the x, so the integral of e to the x times dx would also be e to the x. And then we have our plus c. So So another property that we have here, derivative with respect to x, thank you, of the natural log of x gave us the reciprocal of x. So if I'm going to then undo that, integral of 1 over x times dx would be natural log absolute value of x plus c. The reason I'm throwing an absolute value on here is in the original, I didn't make any restrictions about what x could be. But here, natural log, recall, we have to have a positive argument. Well, really, a positive argument. X has to be greater than 0 here. So we include the absolute value when we're doing the integral. And then similar properties to what we saw with derivatives. Integral of k times some functions. So k is a constant. And again here, we've already got the plus c. Is just k times the integral of f of x dx. Integral of a sum or difference is the same as if I took them separately. So same kind of properties that you saw back in your derivative days. So for example, let's see, we'll do integral of 16 e to the u times du. So that's 16 integral of e to the u du. Antiderivative of e to the u is e to the u. And then we add our plus c. Integral of pi times dx would just be pi times x plus c. So the integral of a constant is a linear, just like the derivative of a linear is a constant. Let's see, let's try another couple. Integral of 9x to the 5th times dx. So 9 integral of x to the 5th times dx. So I'm going to hang on to the 9, and I'll just sort of mentally work backwards on this x to a constant. So instead of dropping 1 from the exponent, I will add 1 to the exponent, which means then I need, in this case, a 1/6 plus c, and then we just do a little cleanup there. So 3/2 x to the 6 plus c would be our integral. Might have a couple pieces. Integral of 23 over x plus 7 e to the x quantity times dx. I just work the terms one at a time. So you can write them out separately, or you can just sort of go through them one at a time. So this would be 23 integral of 1 over x is natural log absolute value of x. Hang on to the 7. Antiderivative of e to the x is still e to the x. And then we add our c. Notice I didn't add 2 plus c's on here. The reason for that, adding 2 constants together will still just give you another constant. So we just need 1 tacked onto the end, not necessarily a plus c sub 1 plus c sub 2. All right, so let's see, here's another good one to practice with. The integral of 18 times the 4th root of x cubed times dx. Now, like our derivatives, our integrals, if we see a radical notation, you need to take one step and rewrite it in exponent notation. So this would be integral of 18x to the In this case, 3/4 power times dx. Don't lose that guy. Hang on to him. Keep the dx. After that, now you're just doing a power rule just like we did back in this other example a couple previous. So I'll hang on to the 18 and then leave a little room and work with my power. So instead of subtracting 4/4, I will add 4/4 and turn this into a 7/4 exponent. So that means I need the reciprocal of 7/4, which is 4/7, and plus arbitrary constant. After that, we just do a little bit of cleanup. So we have 72/7 x to the 7/4 plus some arbitrary constant. So the nice thing about integrals, you can always check them by differentiating and make sure you get back to something equivalent to the original problem. You can always just hit that reverse gear and see if it worked. And let's do another couple where we have to do a little bit of manipulation. So let's try integral of 5 over the cube root of t plus t to the 3/5 power quantity times dt. So this one I do have a little bit of rewriting I have to do before I take the integral. Excuse me. So this would be the integral of 5 times t to the negative to get it out of the denominator, 1/3 to get it out of the radical, plus t to the then 3/5 power, close it up, multiply by dt. So I'll hang on to the 5, leave a little room. Negative 1/3, remember we're doing the antiderivative, so instead of subtracting 1, remember to add 1, bring it up by 3/3. So that would be a positive 2/3. So we'll need a 3/2 there. Hang on to your plus sign in the middle. Do the same thing with the next term. Add, in this case, 5/5, so 1 in the form of 5 over 5, so that's t to the 8/5. So we'll need a 5/8 there, and of course we'll also need a plus c, and then just a little simplifying. So 15/2 t to the 2/3 plus 5/8 t to the 8/5 plus arbitrary constant c. All right, one more together, then I'll have you all try a couple solo. So integral of t by t squared minus 15 quantity times dt. So this one we have some simplifying to do. We need the distributive property. This will turn into the integral of t cubed minus 15t, close up those parentheses, yes you do have to have them, times dt, yes you also have to keep that. So I haven't done any calculus, so I haven't gotten rid of this integral symbol, I haven't gotten rid of the dt. Now that I've simplified, now I'm ready to do the antiderivative. So t cubed is now t to the 4th, so add 1 to the exponent and multiply by the reciprocal. Same deal here, this t is really a t to the 1st. So I'll add 1 to that exponent, multiply by the reciprocal, and add our arbitrary constant. So 1/4 t to the 4th minus 15/2 t squared plus arbitrary constant c. Okay, so I'll pick out a couple that your author had set up. We'll just start a fresh page for these. I'll just take care of these integrals. Integral of 2x to the 2/3 minus 3 over x to the 4th quantity times dx. Let's see, yeah, b is worth trying as well. So again, this is part of your author's you try it problems. So integral of 4 times the 5th root of w cubed dw. C, integral of x to the fourth minus 8x cubed all over x squared, quantity times dx. And part D, we've got integral of 8 cube root of x minus 6 over square root of x, quantity times dx. So give those 4 a spin, see what you come up with, and unpause it when you're ready to go through them. Okay, welcome back. So let's see, this first one we do have a little manipulating to do. So we have integral of quantity 2x to the 2/3 minus 3x to the negative fourth, close it up, times dx. I have not done any calculus, I've just done some algebraic manipulation. So those are ready to go in that format. So hang on to that 2 for the moment. X to the 2/3. We'll add a 1 in the form of 3/3. 2/3 plus 3/3 is 5/3, which means I'll need a 3/5 here. Hang on to the minus 3. X to the negative 4 plus 1, watch your sign work there, is negative 3. Reciprocal there is negative 1/3, and a plus c there. And then just a little cleanup. So 6/5 x to the 5/3 plus x to the negative third plus c. B, not much manipulation to do on this. Hang on to your integral, 4w to the 3/5 power times dw. Hang on to your 4, w to the 3/5 plus 5/5 is 8/5. So there's your 5/8, the reciprocal, plus c, and then a little cleanup. So 5/2 w to the 8/5 plus arbitrary constant c. C, a couple little reminders on that one. Same thing that allows you to just glance at 1/7 plus 2/7 to call out 3/7. You're mentally adding the numerators, keeping the common denominators. If you're allowed to put them together, you're also allowed to pull them apart. So integral of x to the fourth over x squared minus 8x cubed over x squared. Close the parentheses around it and hang on to your dx. One more step in the simplifying. So this is integral of x squared minus 8x, close it up, times dx. And then we're just using our power rule there. So x squared is now x cubed, and I'll need a 1/3 for a coefficient there. And a minus 8. X to the unwritten first power is now x to the second power. So I'll need a 1/2 there and a plus c. So this would be a third of x cubed minus 4x squared plus c. D, a little bit of manipulation needed before we integrate. So integral of 8x to the 1/3 minus 6x to the negative 1/2, close it up, times dx. So negative got it out of that denominator. 1/2 power got it out of the radical notation. So then we'll hang on to the 8. X to the 1/3 is now x to the 4/3, so we'll need a 3/4 there. Hang on to the minus 6. X to the negative 1/2 is now x to the positive 1/2. Reciprocal of a half is 2. And we'll add c. So then we have 2 by 3 or 6. 6x to the 4/3 minus 12x to the 1/2, and then plus arbitrary constant c. All right, so part E, didn't quite have room on this page, so I'll put out part E, and then we'll hit a couple of quick applications here. So part E, we had integral of x squared minus 2 by x plus 3 quantity times dx. So go ahead and pause that, see what you can do with that. Welcome back. So here we'll just FOIL it out and turn it into a sum and difference problem. So we have integral of x cubed plus 3x squared minus 2x minus 6, close it up, times dx. So just FOILing it out. first, outside, inside, last. No more manipulation needed. We can just do the power rule from there. So x cubed is now x to the fourth. We'll bring a 1/4 along there. That way when I multiply the 4 and the 1/4 together, we get that nice, neat, pretty implied 1 that we had in front of the x cubed. Hang on to +3. X squared is now x cubed, so we'll need a 1/3 there. Hang on to the -2. X to the first is now x squared. We'll have a 1/2 there. And derivative of a linear is a constant, so integral of a constant is a linear. And then we'll throw on our plus c. So then just a little bit of cleanup, make it a little prettier. A 4th x to the 4th plus x cubed minus x squared minus 6x plus arbitrary constant c. All right, so a couple of applications. The first one deals with initial conditions. So we're going to find the equation of function y equals f of x with two properties. dy of dx is -3x, and f of 0 is -5. So if dy over dx is -3x, then dy is equal to -3x times dx, and we just integrate both sides. So integral of dy is going to be y. Hang on to the -3. X to the first is now x to the second, so we'll need a 1/2 there. And plus arbitrary constant c. So far this was just like saying find the integral of -3x. No big deal there. We can go over the function notation. So f of x is -3/2 of x squared plus arbitrary constant c. The only new thing that this problem has is the initial condition that f of 0 is -5. In other words, they're saying, okay, of all of the different graphs of y equals -3/2 x squared plus a constant, this one goes through the point 0, -5. So we'll replace the f of x with the -5, the x with the given value, in this case 0. So -5 is 0 plus c, so c here is -5. So then we can tell them that the function is f of x is -3/2 of x squared minus 5. So this one has both properties. Its derivative is a nice, neat, pretty -3x, and it goes through the ordered pair 0, -5. All right, so the next one, we get to play with a nice little business application. So let's say they give us the marginal cost. It's given by c prime of x, 7/10 of x squared plus 4x plus 1 with fixed cost of $6,000. So we're going to find the cost function, and then we're going to find the cost to produce, what did I pick out? 1,000 units. So x is our number of units. and cost, unless otherwise stated, is going to be in dollars. So marginal is the derivative of the cost, so the cost would be the antiderivative of the marginal. So we'll do the integral of 7/10 of x squared plus 4x plus 1, close those all up and multiply by dx. So we'll hang on to the 7/10. X squared is now x cubed, so we'll need a 1/3 here. Hang on to the plus 4. X to the first is now x squared. We'll need a 1/2 there. And antiderivative of a constant is a linear. So c of x would be 7/30 x cubed. So 7/10 over 3. I don't want to use a decimal within a fraction, so we just hit top and bottom by 10. 10/10 is worth 1. So 7/30 x cubed plus 2x squared plus x plus c. Now, this plus c, though, matters. They did tell us we have a fixed cost. So remember in business what a fixed cost means. Basically means that if you have your factory open and instead of using it to make whatever it is that you're selling, you set up a pool table and spend that month playing pool, you made 0 units. That landlord still wants the money at the end of the month. Landlord wants the same amount of money no matter how many units you made or didn't make that month. That's an example of a fixed cost. Variable costs, things like electricity. If your machines are working harder, they're pulling more juice, your electric bill will go up. Production goes down, you're not using as much juice, your electric bill could go down. That would be a variable cost. But fixed cost, here is 6,000. So the cost, even if I made 0 units, is equal to 6,000. So this is like an initial condition from that previous problem. So we'll just say, okay, our y value is 6,000 when our x value is 0. So C here is 6,000. So then C of x would be 7/30 of x cubed plus 2x squared plus x plus 6,000. So then to find the cost of 1,000 units, we're just finding C of 1,000, and that lands us at approximately, let's see, 235,340,333 and 33 cents. So that is in dollars. Okay, so some problems to try out. Let's see, we are in section 5.1. I would recommend 1 to 23 on the odds, 43 to 69 every other odd, 81 and 85. Those are a couple of application ones at the end there. As usual, if you have questions, please get in touch and stay safe out there.